And it's a real pleasure this morning to have Professor Bing Li speak to us. And Bing joined the Department of Civil and Environmental Engineering at the University of Western Ontario as an assistant professor in 2021. And he is the research director at the Geotechnical Research Center. And the interests there are in geomechanical model calibration, slope stability in permafrost, and induced seismicity in mining, energy, and volcanic settings. Now, prior to Western, he was a postdoctoral fellow at the Seismological Laboratory at Caltech, and he has consulted as a geophysicist with Zanskar Geothermal and Total Energy. His PhD is from MIT in 2019, and that was on high-resolution imaging and acoustic emissions in granite and shale fracture processes. His BA, his Bachelor of Science, was in mineral engineering from the University of Toronto in 2013. So, Dr. Li, it's a great pleasure to have you speak this morning.
Thanks so much for the introduction. Let me get my slides up. Okay. Are we seeing the correct version? Okay, I'm getting a nod from Omar, so I'll get started. Okay, so yeah, once again, thank you so much for the introduction. Thank you for inviting me to give this talk. The focus of it really is sort of trying to put together this story of when we think about this induced seismicity that we can observe, thinking about what it actually means in terms of the fractures that we've developed and how to incorporate that with other data sources, for example, remote sensing. And I'll talk a little bit about machine learning applications to some lab data we can put together. Of course, I wanted to acknowledge supervisors, colleagues, now students that have helped and inspired and for whom I've learned so much all along this journey. With that, we'll get started. So I'll first talk about sort of the case of essentially an ideal world, right? When we're thinking about unconventionals, we're thinking about geothermal, we're thinking about carbon storage, nuclear waste storage, anything involving the subsurface. Ideally, in a perfect world, again, what would we like to have is basically some idea almost of CT level resolution everywhere on Earth, right? Data limitations aside and all that. It would be great if we had micrometer, even nanometer scale resolution of all the mineralogies, all the pores, all the pore fluids, all the structures, that being joints, discontinuities, faults, what have you, everywhere in our rock mass, right? We'd be able to do so much with them. Unfortunately, that's not quite what we have. But what we do want to have, and I'm borrowing an expression from Giovanni Grasselli at U of T, is basically we would like to have basically Superman X-ray vision of our rock wherever we, right? That's sort of ideally what we'd like to be. Obviously, that's not really what happens in real life. So I wanted to first talk about what we do have, just as sort of a brief overview. Of course, one of the big sources of data that we have is core logging, right? Actually getting the rock out of the ground, looking at mineralogy. This is where we get CT scans, right? We get CT scans from these cores that we can get. We can get a good sense of where the structures are, where our geological domains are. I believe this is one from Australia, and we have a pied butchered bird for scale. This is not too big of a core. And of course, with core, we also have borehole geophysics, and we have televiewer imaging, right? So that gives us a good sense, once again, sort of in a more automated sense, where our geological domains are, where our structures are present. So that's from the borehole perspective. From geophysics, we can, of course, have seismic reflection, which gives a sense of, once again, where our geological domains might be, as well as a sense of sort of inferred structures that we might want to be concerned about. Of course, the advantage here is that we can have this in a continuous spatial domain, as opposed to boreholes where we're looking at point sources within the subsurface. right? If we're lucky, we might even have something like ambient noise tomography, right? This is an example from not an active geothermal exploitation scenario, but the Long Valley caldera in California, where with ambient noise tomography, we can get, for example, a sense of where this low shear wave velocity zone is that corresponds to what was previously this giant magma chamber that's now sort of crystallized and is cooling, but nevertheless represents this zone of sort of elevated heat flux, basically, that we could exploit, barring all the other technical limitations and issues. So the focus of this talk, of course, is mostly on the two aspects that I'm showing on screen here. Nowadays, we can get very good microseismic monitoring data, right? So this is a public one from Western Alberta from David Eaton's group at University of Calgary. They had 69 geophones and seismometers that were put out, and they were able to detect, depending on the catalog, up to 20,000 events over a month, corresponding to this unconventional stimulation program that they did. And so from this, we can get a whole wealth of information, right? We can get the locations of the events, we can get the time of the events, we can get their magnitude, we can get their focal mechanisms. The focal mechanisms, we can get stress inversions if we're interested in that. We can also have stress drops, for example, to look at sort of get a sense of the fault dynamics. And of course, corresponding to that, we can also get, for example, inSAR deformation from satellites, which tries to sort of complement this microseismic, because as we know, microseismicity, especially in materials like shale, there can be a lot of aseismicity, right? Just because we know that we have, this fault that's being activated, these hydraulic fractures that are being activated, there are certainly regions that are being activated but are not represented by seismicity. And I'll try and get into this sort of during this talk. And of course, as I said, these sort of ground deformations try and give us a more, you could say, unbiased view of what's going on in the subsurface. And I'll talk a little bit about how we can sort of use that to do inversion, to constrain geomechanical models, in this case for a geothermal site in Idaho. So I'll first start at the lab scale. Omar will be very familiar with this. This was done at the MIT Rock Mechanics lab under the supervision of Albert Einstein during my PhD. And this is sort of, I'll be talking about, again, this idea that we can detect all these microseismic events when we generate fractures of whatever kind we're interested in. But what we're really missing at the field scale is to be able to directly say, okay, where are these fractures? How far are they going? What is the relationship between these microseismic events and the fractures that we can actually see at the lab scale? And I'll also be talking about, of course, deformations, which ties into this, again, this idea of remote sensing. How does then this these deformations relate to the fractures that we can observe, and also the microseismicity? So the first set of data experiments that I wanted to talk about is from a very simple experimental setup. This is a 4-point beam bending set of experiments. Basically, you load a beam of rock, in this case, both granite and shale, simply supported, and then you basically generate indirect tensile fractures without there being any fluid. So these are essentially only stress-driven tensile fractures. This is sort of trying to establish a base case of the this kind of relationship that we want to study. So in this case, what we have are two cameras that are imaging the specimen, in addition to, of course, the acoustic emissions or nanoseismicity, what have you. The first one is this sort of very general scale camera that's looking at the whole specimen, or at least the whole length of the crack, where we get sort of general idea of where it's going and how far it's gone at a given time. And then the second one is a very detailed sort of microscope view the tip of this pre-existing notch, where we can look at sort of closer to the grain scale what's actually happening when these fractures initiate, and then sort of the beginning of their propagation. So here I'm showing the this sort of microscope view. You'll note that the scale is quite small. So the viewing window is about 1.4 millimeters. So we're really just looking at, the first few grains in terms of granite that are being fractured under these stresses. So I have this for granite, and I also have this for an opalinous clay shell from Monterrey in Switzerland. So the two things that I really wanted to point out in terms of this material is that if we look at the granite, what you'll see is that there's a lot of these conjugate shear fractures. So there's these sort of classic, when you think of the Coulomb envelope, you have these conjugate shear planes that can form. These are very prevalent when we look at the granite fractures microcracks that we can see. Whereas if we look at the shale, it's sort of a lot more unimoto, if you will. There's only this one set of planes. You don't really see that other conjugate set of planes. And we interpret that as being basically, we get these en echelon shear cracks in the granite, which are actually forming in shear, right? You'll remember that the overall stress state is supposed to be basically a tensile stress state, but what this is suggesting, and I'll sort of back this up with the acoustic emissions data, that there's a significant element of shear, particularly in the granite when we look at sort of this micro grain scale. Another thing that I wanted to note is that the arrows, which are showing the displacement vectors, are essentially a lot more ordered when we look at the granite compared to looking at the shale. The granite is basically a very clear opening mode, whereas the shale exhibits sort of a much more disorderly displacement field. And we posit that this is essentially related to this process zone, which is a zone of inelasticity ahead of the crack tip, and I'll talk about that in a second. Sorry, I forgot to mention that the color in all of these plots is the epsilon1. So it's, in this case, we're using mechanical people's convention. So the epsilon1 is the most tensile strain, not the most compressive strain in this case. Okay, so talking about this process zone, then this is just a frozen snapshot in time of, once again, this strain field. Hi, yes, question, Professor Bazant? Okay, we can also have
might
discussion.
I suggest that we save the questions till the end, please. If you have a question or an observation, please use the chat.
Okay, yeah, that's fine. Okay, so we'll have discussion at the end. So thinking about this process zone, here I'm showing just a given snapshot in time of the granite and the shale. They're sort of comparable in terms of their the percentage of the peak load. And so if we look at the granite, you can see that there's this sort of much wider zone of strain that's induced in the granite, as opposed to the shale, where really all we're seeing is this sort of single path of the fracture, these microcracks that are being outlined by the strain map. This is to say, what we believe is happening is that this granite is generating a much larger process zone, this area of inelastic deformation, compared to the shale, where, at least visually, all we're able to observe are the actual microcracks themselves. The magnitude of the inelastic deformation, at the very least, is much smaller in the shale compared to the granite material. Okay, so promise we would look at the acoustic emissions, microseismicity, nanoseismicity, what have you. This is what I'm showing here. On the top row are these acoustic emissions for the granite, and in the bottom row are these acoustic emissions for the shale. So the first thing I wanted to point out is basically, if you look at the area in which these acoustic emissions are happening in the granite, you'll see it's a much more compact, concentrated zone. It's a very sort of well-defined zone that corresponds pretty well to the path of the fracture. And then if you break these events down by now the mechanism, so if we look at the shear dominated acoustic emissions versus the tensile dominated acoustic emissions, we can see that the tensile events are even more well clustered, right? When we look at the tensile events, they essentially map out the path of our overall fracture. If we look at the shale, now things are a lot more scattered. Well, not just scattered, but first of all, that the quantity of acoustic emissions we observe in the shale tends to be a lot lower. And this is most likely related to the nature of shale being a more rate strengthening material, as they call it in geophysics, which is to say that it tends to produce much lower seismic energies for a given amount of energy input into it. So there are much fewer events that we observe in the shale, but also if we look at the locations of them, we can see that they're sort of more diffuse throughout the medium compared to the granite. That is to say, if we're thinking about, once again, this cloud of microseismicity you see, it appears, at least for this case where we're fracturing through intact material, the events are much more closely tied to the eventual location of fracture itself in granite compared to what we see in shale. And then, as I alluded to earlier, when we look at the proportion of what's called double couple focal mechanism, you can view this roughly as sort of the amount of shear that we see in our acoustic emissions. We can see that the granite exhibits about half of its energy in a double couple mode, whereas the shale only exhibits 42% in this case. Generally a lower proportion of shear, which is coming back to this idea that when we think of the microcracks that are being generated in these two materials, the granite has a higher tendency to shear, at least on a grain scale compared to the shale. So finally, we can sort of try and do a quantitative comparison between both the imaging data that we can grab as well as the acoustic emissions that we do. So the first thing we can look at is basically a very simple, okay, from the image, we can sort of look at how far the crack tip is from the original notch and how far this process zone is from this notch. And then for the acoustic emissions, we can also measure the distance of any event from this pre-cut notch that acts as the stress concentrators for these fractures. So on the left, I'm showing a plot of this distance from the notch tip over time for the granite. And on the right is the same plot, but for shale. So the red line on the top here is showing this extent of the process zone away from the notch tip. And then this bottom line is showing the extent of the crack tip itself from the notch tip. And I'm not showing the concentration plot here, but basically what this plot shows is that the majority of the events that we actually detect occur in this process zone. They occur between the crack tip and the furthest extent of the process zone. That is, most of the events that we see, at least in the case of this beam bending, occurs in the process zone and not in the area that's actually being activated, if you will, right? There's very little permeability that you get in a process zone because there's still some cohesion that's keeping your contact surfaces, or so your surfaces of your crack together. But when we look at the shale, this is quite different. So if you look at the shale and you look at the locations of the events in relation to the process zone, as well as this crack tip, you can see that there's not this clear sign that the events happen within this process zone, right? They're sort of happening behind the crack tip, a little bit ahead of the crack tip, but primarily sort of throughout the whole volume of the crack is where you get these acoustic emission events in the shale. So that was talking about this beam bending where we don't have fluids involved. It's a purely dry stress-driven fracture. Now we can talk about hydraulic fracturing experiments. Once again, we've done this in both granite and in shale. And so once again, what we've done is we painted sort of this area ahead of the tip of this pre-cut notch. This is a scale of 1 millimeter. And again, we can get these sort of very detailed view of the growth of these microcracks as the pore fluid pressure is increased. I want to note that in the case of this set of experiments, the bedding planes in the shale are vertically oriented, like so, whereas in the previous set of experiments in the beam bending, the bedding planes were actually horizontal in the case of the shale. So I want to talk about 4 experiments in this case. So 2 of these experiments are done in Barre granite, 2 of these experiments are done in opalinaceous clay shale. And what we can see are, in blue is the pressure over time. So these experiments were done at a constant injection rate. So we get roughly a linear pressure over time, except when it comes to materials that sort of have some degree of fracturing in the early stages, and then these fractures sort of slowly propagate throughout the experiment, which is what happens in this experiment here. And then the dots in red are showing the amplitude of our acoustic emissions events. As you would expect, it sort of generally ramps up in amplitude over time. So once again, this is a similar kind of plot as I showed for the beam. This is once again the sort of microscope type of imaging that we can get. And this one is, I'm showing an example in granite. So again, what we'll note is that we see this very clear development of sort of parallel en echelon cracks early in time, and then these eventually get connected by their conjugate en echelon shear cracks with the increase in pressure. So this T norm is essentially a percentage, where T norm of 1 is where we have peak pore pressure, and 0 is basically the beginning of the experiment. So yeah, once again, the granite shows, I think, a very clear sort of idea that we're getting really these en echelon cracks in the hydraulic fracturing, just the same as we saw in the beam bending experiment. Now I'm showing the same sort of plot, but in the opalinaceous clay shale. And so something that's very interesting to see here now is that, first of all, we don't really get these en echelon cracks, right? These are now primarily bedding plane driven. You recall that I said that the bedding planes are essentially close to vertically oriented in these experiments. And what's very interesting is that you'll see that there's actually another bedding plane that sort of started to dilate here. And then later in time, we had 2 bedding planes on either side of this crack tip, right, that begin to dilate. But over not too long of a period of time, one of them sort of takes over and becomes the dominant hydraulic fracture that then continues to propagate. And you see that this one that eventually dominates is not the one that was first dilated, right? This is sort of alluding to this idea that it's sort of still a stochastic system in the beginning, that there's multiple candidates of where the hydraulic fracture might go, and then one of them sort of becomes dominant towards the end. And so what we can then superimpose, as I've done here, is what the actual images of the surface of the rock looks like in relation to the observed cracks that we see. So here in the shale, the grain size is sort of still quite a bit smaller than the resolution we have on the camera. So we can see that it sort of generally follows bedding planes, as I would expect. Or sorry, we can posit that these generally follow bedding planes, but it's hard to sort of exactly see what's going on. But when we come to the granite, right, we can see exactly the grains that are being activated, which is quite cool. So in the case of this granite, for example, it actually avoids this dark grain, right? You can see, eraser. There we go. So we can see that this these 2 branches of microcracks actually don't connect, and they're separated by this dark grain here, which I presume is sort of a much tougher material that these microcracks cannot propagate through. And in a lot of cases, for example, here as well, it tends to sort of follow this intergranular crack around tougher grains, at least what we can see from the surface of these materials. Now we can, again, sort of try to relate this to the acoustic emissions or microseismicity, what have you. So what I've done here is these two plots are for granite, and the black line represents the rate of acoustic emissions that we can see, the rate of acoustic emissions that were detected throughout the experiment. And then the dotted lines represent the shear deformation along 3 different points along these microcracks. And really the thing I wanted to point out is that when you look at the magnitude of these displacements, when thinking about both the shear and the normal displacements, we can see that they're comparable in magnitude, right? We got similar amounts of both shear and normal deformation along these microcracks and granites, and that when we look at the acoustic emissions rate, it sort of slightly precedes the amount of detected deformation, which makes sense because when you try and back calculate sort of the amount of displacement that corresponds to individual acoustic emission events, that tends to correspond to the order of nanometers, right? So the acoustic emissions is in many ways much more sensitive than what we can get with our imaging techniques. It's sort of a generally similar story with this other granite experiment. Again, we get sort of comparable magnitudes of the shear and the normal deformations, and it's sort of slightly preceded by this rate of elevated seismic energy release, if you will. Now, this is where it gets interesting, is when we compare this to the opalina's clay shale. Now you see that these normal deformations are much larger in magnitude and happen earlier than the shear deformation, right? This is once again coming back to this idea that the opalina's clay shale, when we develop these microcracks, they're primarily happening in tensile mode and not so much in the shear mode. And then comparing it to the acoustic emissions, in this case, it seems like there's less of sort of they occur roughly at the same time. The acoustic emissions don't really precede the deformations in this case, and we posit that's because, once again, shale tends to be a lot more aseismic. It tends to be a lot more rate strengthening. So because our detection threshold for the acoustic emissions is a static value, we're only able to detect larger magnitudes of acoustic emission events in the shale, essentially. So that's that. Now I just wanted to talk about sort of some work we've been working on recently in terms of, we have this large database of acoustic emissions as well as pressures as well as images. What applications of machine learning are there that we could sort of think about in terms of trying to, well, how can machine learning add value to these large data sets that we've collected over time? So here I'm talking about a set of granite hydraulic fracturing experiments that have been done by Bruno Gonçalves da Silva, who was taken from us far too early. May he rest in peace. So we have a set of about 20 hydraulic fracturing experiments in granite. The main differences between experiments is that the orientation of the 2 pre-cut notches is varied between experiments, and also that some experiments are preloaded for a given axial stress of 5 MK, and others are sort of at ambient. There's no axial load on them. So the work that I'm going to be showing is primarily focusing on sort of 14 of these experiments where we have really good acoustic emissions data. And the first application that I want to talk about is sort of predicting this breakdown time, right? So when I'm talking about breakdown time, is essentially the the time of where this pressure drops essentially to zero. The reason that this happens is basically once the fractures rupture in these granite specimens, they reach to the edges of the specimen, and we have total loss of fluid from the system. So anything sort of after is not comparable to what you might see in the field. So really this idea is, okay, we have all these acoustic emission data. Can we use this? Sorry, these are the black dots, the acoustic emission magnitudes over time. Can we use these acoustic emissions data to predict the time that we have this breakdown, right? Where we have these large scale fractures that rupture the specimen. So classically thinking about how to predict failure in these kinds of systems, what we've seen is essentially, or what the literature shows is that basically you get this acceleration of the seismic energy rate to when the system is approaching failure. Basically, it sort of roughly has a linear trend beforehand, and at some given time, it begins to accelerate with a power law distribution, sorry, a power law acceleration. But the issue is this only really happens 3 seconds ahead of time, right? And it's also very difficult to basically do this in real time, right? You don't know that it's become this sort of power law mode until, say, you're halfway through, right? Similarly, people have done sort of an inverse. They've taken the rate of acoustic emission, or sorry, this comes from the slope stability world where they monitor displacements of their slope. They turn that into velocity. They take 1 over velocity. And they make the argument that if you take this sort of 1 over velocity, you can predict the time of the failure of the slope. It turns out you can also do this in the context of acoustic emissions. If you look at the rate of acoustic emissions, you take 1 over that. The time that that reaches 0 is sort of roughly where you have this breakdown time. But once again, the issue is this technique only really works in our data set at least 20, 30 seconds ahead of time, right? So we're trying to apply machine learning to this problem, looking at the actual waveforms, right? We have this rich time history throughout the experiment of what these waveforms look like, all the way from the beginning experiment to the time where we have breakdown. So this is inspired by some work done at the Los Alamos group, where they have this double direct shear device. And so with that, they're able to generate cycles of basically fault slip. Sorry, I'll show it this way. They are able to generate these cycles of fault slip. And within the same experiment, they can generate tens of these cycles, right? These are sort of an example of one cycle where the shear stress gradually increases until you get a discrete rupture event. And they use a random forest, which is sort of, in fact, it was created, I think in the 1960s or the 1990s, in the 1990s. And what they're putting in is they take their acoustic emission time series, and they plot out a bunch of statistical moments, for example, the variance, the kurtosis. They also look at thresholds over time. And they calculate, I think it's a total of 64 parameters of interest from the original acoustic emissions data. They feed this into the random forest, and they use that to predict the time of their next slip event in this case. So the main issue when it comes to doing this for hydraulic fracturing is for a given sample, you only get one set of hydraulic fractures that come out, right? You only get one breakdown event that happens. So that's really the benefit of our data set here. We have at least 14 different experiments done under roughly similar conditions that we can use to explore the application of this model to breakdown time in hydraulic fracturing. So this is sort of roughly of an idea of what the voltage amplitude looks like in the first, in this case, 0.1 seconds before our large rupture event. And so once again, we're trying to tie this sort of the characteristics of this time series to this time of breakdown that we can detect, or that we can label for every given experiment. So basically the question is, we can set up all this model, we can put it in, we can train it. How well does it work? Well, I would argue it works pretty well, actually much better than I would have ever imagined. We get an R squared of 0.98, where 1 is a perfect one-to-one prediction, 0 is no ability to predict whatsoever, no correlation. And so what I'm showing in these plots here on the x and y axis, the x-axis is showing the true time to failure. So failure here refers to the time of the breakdown. So we're looking at a whole 1,000 seconds of the experiment here. And so we can see this is really good correlation when you look at the density, that we're able to predict the time of this failure even 1,000 seconds ahead of that failure event, which I think is quite impressive, given that the other techniques I was mentioning, we only really get a sign that this system is approaching failure 10, 20 seconds ahead of time. And then if we take the average difference between this predicted time to failure and the true time to failure, we get a difference of about 4 seconds, which once again, I'm pretty pleased by, and honestly positively surprised that we're able to get this kind of result. Obviously, we can also plot this per experiment, and you'll see that the majority of experiments actually look even better than the overall plot. It's really this one experiment that sort of seems to be quite difficult to predict. We've tried to sort of probe into why this might be happening. And it seems that there were just very few events. There was a lot of acoustic emissions noise in the experiment, but not that many detectable events. So we suspect this was just sort of we hadn't bonded the sensors properly or something, and that caused it to be very difficult to predict. So that's that. One of the big benefits of this sort of random forest over deep neural networks especially is that we can also probe why the model makes the predictions that it does make. So here I'm showing the list of features that were fed into our model, or the top features in terms of their importance, and then the x-axis showing the importance, or how much weight is assigned to this feature for a given our model. And you can see that the mean has the highest weight or importance in these predictions by far, which I think makes sense because really the average energy level of our system is the best indicator of how close it is to failure, how close it is to instability. So I think that makes sense. But if you look at the next ones, you see the skewness, the kurtosis, and the variance all have pretty big importance in terms of predicting this failure. So this is to say that there's a lot to be extracted from not just the average level energy, but also sort of the more finer details of its distribution, if you will. And so there's room to obviously improve this model a lot more. This is, again, not even sort of this modern machine learning architecture that we think about these days. So we're still exploring whether we want to go further with this. The second sort of application of machine learning we've been exploring is, I've been alluding sort of throughout this talk to sort of this idea that talking about tensile and shear cracks. And that similarly in the acoustic emissions, we can separate out shear from tensile dominated events. And so in seismology, this is reflected as the moment tensor, which is sort of analogous to the stress tensor. There's 6 independent components. And so classically, to invert for a moment tensor from microseismic data, you want at least usually a lot more, 6 observations to be able to constrain this tensor. You can obviously do it with fewer if you do full waveform inversion, which is really sort of what we're trying to get at with our machine learning model, is to see what we can get out of this moment tensor using just one sensor. This is for the case where, first of all, you want rapid characterization of the kind of events that you're getting, but also in terms of sometimes you have fewer sensors than you would like, or fewer stations than you would like, or you have issues with noise. What can we do with just one sensor, acoustic emission sensor in this case? So basically what we did was we collected a bunch of acoustic emission data that we collected throughout my PhD, both from the beam bending and from various types of hydraulic fracturing. And we collected over 300,000 acoustic emission waveforms as training data. So that's on the data side. That's the input. What do we actually get? What are we actually using as an output? So in this case, we're not trying to solve for the full moment tensor. We'll try that, or we're trying that as we move forward in time. For now, the task we've simplified to a much more simple one, which is just to say, okay, given a waveform that we can detect, did that waveform originate from an event that exhibited contraction or compaction, or did it exhibit dilation or volume increase? And so this idea of dilation makes a lot of sense from a mechanics perspective. It's basically mode one. The contraction is something that's not strictly described in mechanics, but it is something that people, particularly in mining, see, what they call strain burst, which is essentially a crushing of grains at stress concentrations. So basically, this acts as the label for each given waveform. We label it as, did it come from a contraction or did it come from a dilation? So that's the data input, data output. What does our model actually look like? What machine learning model are we using? So this is one that was trained on field data by Zach Ross at Caltech. And so originally it was trained on 2.4 million earthquakes in Southern California. But I want to note that the task it was trained on is not the same as the task we're using here. It was not originally trained to detect the volume change at the source. It was only trained for the much simpler problem of saying the first motion, does it go down or does it go up? So you can see it's a very related event, right? The way we get these moment tensors is by looking at the first arrival, and if we're from inversion, we look at the rest of the wave train. But basically, this is a network that was trained on a lot of earthquakes from Southern California, and we want to sort of leverage the fact that it's already been trained on so much field data. Right? So these neural networks, they're called convolutional neural networks. They have sort of two main components. They have a feature extraction part and a feature interpretation part. And so what we've done is basically we've tried two things. We've tried training the model from scratch. So we delete all the pre-existing model weights and we train it using just our data. And we've also tried taking the pre-existing model weights from this model and keeping this. We're only retraining this interpretation, right? Because we're changing the tasks that we want to solve, but we're actually, this neural network knows a lot about what these wiggles are, what they characterize, so we're keeping that constant. So turns out, if you look at just our lab data, our testing lab data, both models perform similar. We get about 86, 87% performance. But then when it comes to a set of field data that were reserved for testing, these are from a series of mining events that happened in the Western US, you can see that when we retrain, where we retain the pre-existing model weights, we get much better performance compared to training it from scratch. Right? This is this benefit of retaining this information that was originally trained on from these 2 million waveforms from Southern California. Of course, we also want to try and mechanistically, or at least qualitatively, look at why we're getting the performance that we get. What can we say from the characteristics of the waveform themselves? So here is what's called a confusion matrix. So these two boxes basically refer to compactive events that were correctly predicted as compactive, and dilative events that were correctly labeled as dilated. So one key thing that I wanted to point out here is that when we look at the energy, so this is the power spectrum, or sorry, the spectrogram average over all the events in our laboratory test set, we see that the compactive events have this sort of very impulse type nature. There is very high energy at a very short amount of time, right at the first arrival. Whereas when we look at this, these dilative events, we get this sort of longer coda basically that there's more resonance along these microcracks, which is similar to what has been seen in, for example, volcanic tremors. When we come to this field data, again, these are mining data that the model has never previously seen before. We get the similar sort of trend that the compactive events have this sort of very short duration impulse type of energies right at the beginning, whereas these dilative events have sort of this longer coda after the first arrival. So that's two applications of sort of machine learning to this kind of data set that we've been exploring. Finally, I want to talk about field case where we use inSAR to constrain a geomechanical model in Idaho. And so one of the interesting features of this geothermal site is that, as far as we've seen from the literature, the cold water is actually being injected into a shallow reservoir, about 500 meters below the surface, and the hot water extraction is actually being done on a deeper level. So the extraction is on a deeper layer, the injection is being done on a shallow layer. Intuitively, you would expect then that the basement would be stabilized because you're actually decreasing the pore pressure, which should increase your effective normal stresses, right? But interestingly, that's not what happens. There's actually a lot of induced earthquakes that happen in the basement, even though this production is nominally happening within this sort of deep reservoir, which is very interesting, right? This is sort of counterintuitive to our general understanding that you need to elevate pore pressures to generate induced seismicity. So luckily, we're able to, or Mustafa Koshmanesh, who was a fellow postdoc at the time, was able to gather a lot of inSAR data from the same site, which is what's shown on the left here. So the color is indicating ground deformation rate. So red is showing uplift, and then blue is showing subsidence. So as you would expect, this is consistent with a shallow injection, right, which creates a much smaller concentrated bulb of uplift, and then deeper production, which is generating the sort of larger zone of more diffuse subsidence. So we wanted to use this inSAR to try and study sort of what might actually be going on, what's causing this basement seismicity, even though our injection is shallow, right? And so there's two mechanisms that are most likely at play here. The first is this idea of pore pressure diffusion, which is the very straightforward, you have fluids being injected to subsurface, these fluids elevate the pore pressure near the borehole, and this bulb of elevated pore fluid diffuses throughout your medium. The second thing, of course, is pore elastic stress, and we suspect that this is what's actually causing this seismicity that we see in the basement, right? Basically, that if you insert a volume into your rock mass, you get a far field elastic stress change in the stress tensor as a response to this change in injection of mass into the medium. So here we're using a very simple pore pressure 2D line source pore fluid diffusion model, and also a very straightforward pore elastic stress model using the Gutzma-Khrushchev solution. And so the benefit of using these sort of semi-analytical solutions is that they're very fast, right? We can basically perform an inversion for the parameters that we're interested in to really calibrate a model that we're confident in, right? So what do we have as data? We have the injection rates, or at least a sense of what the injection rates are from public data, and we have a set of hydromechanical properties, permeability, stiffness, compressibility, that ideally we want to calibrate, right? So from that, we can go to a model pore pressure field, which is shown for the injection here and the production here. And from this pore pressure distribution, we can reach a modeled surface displacement, right? We can predict the surface displacement given this pore pressure diffusion, or sorry, this pore pressure and pore elastic model. And then we can compare that to what we actually measure using inSAR, right? This is really the benefit of having this inSAR deformation, is we're actually able to calibrate, or we're able to measure the performance of our model. And so we can compare this model to this measured surface displacement until we reach a point where we're satisfied. And then we can tweak these hydromechanical parameters until we're satisfied that we get a good match between our model and our measurement. And only then do we have the confidence to then look at the stresses in the basement, right? We can then begin to use this model to think about what are the stress changes in our basement that are likely related to the induced earthquakes that we see. I just want to talk very briefly, I think I'm close to time anyway, that flow, it turned out flow anisotropy is very important for this site that we're looking at. It was only with the incorporation of anisotropic permeability that we're able to get this sort of elongated bulb of surface deformation that matches well with this sort of elongated bulb of uplift that we see in the inSAR data. Now we can then, once we're satisfied that our model is well calibrated and is a good reflection of the physics that we're interested in, we can then look at the stresses, right? And so what we can do is I've plotted in this here, or sorry, I'll start with this plot here. The color is now representing this change in Coulomb failure stress in the basement. Red indicates an increase in the likelihood of slip. Blue represents a decrease in the likelihood of slip. And we were very satisfied, or we were happy to see that when you look at the induced earthquakes, which are shown in black, they almost all happen in zones of elevated Coulomb failure stress, which is a very good sign. And then if you look at it over time, which is what I'm showing here, you can see that there's sort of some critical level of stress that may be needed to trigger these earthquakes, which are what's shown in gray. Of course, we can have a much more detailed look of that. So this plot here is showing basically the change in Coulomb failure stress at the time and location of any given earthquake. And we've separated this into the basement as well as the overlying sediment. And when we plot a histogram of these stresses required to activate it, we can see that the stress required to trigger these induced earthquakes is very low, right? This is on the order of 20 kilopascals, both in the basement and in the overlying sediment, which is to say, in this case, it seems that the rock mass or the faults were very sensitive. They were very close to a critical stress state. So that comes the end of sort of this discussion here, talking about how we can use sort of inSAR deformation to constrain geomechanical models that we may be interested in. So in summary, going from the lab scale to machine learning to the field scale, we see that granite tends to generally exhibit a lot more shear microcracks, at least at the scale we're looking at. And when we think of the nanoseismicity, that tends to occur within just the process zone. So the majority of the nanoseismicity acoustic emissions happen ahead of the crack tip and not in a zone that's already fully expressing high permeability. But when we look at the shale, it tends to exhibit fewer shear microcracks. It tends to be more directly in tension. And the process zone appears to be a lot smaller in shale than it is in granite. I think the machine learning shows that there's a lot of data within the waveforms that have a lot of potential to add value to understanding the subsurface. I showed an example first of predicting the breakdown time, and then also looking at the volume of the source using only a single sensor. And then lastly, I've shown throughout, of course, that using imaging gives us direct data of what's happening along these cracks, but that only works, again, at the lab scale, right? inSAR is sort of, in a sense, the equivalent for the field scale, and it's I think it's a wonderful tool to be able to serve as somewhat unbiased data for what the physics are actually occurring in the subsurface. So with that, I think I'm just about at time. I'm happy to stick around afterwards for questions as long as people are interested.
We do have a few questions. Thank you very much, Bing. Very, very intriguing and informative. Professor Bezant he's had his hand raised for quite a while. Please go ahead.
Yeah, actually, it was my mistake. I somehow hit it. But I do have a significant question. First of all, Dr. Lee, excellent work and excellent presentation. But there is one significant consequence of the gap test, GAP test, that we developed at Northwestern University, which shows that under crack parallel compression, which is non-singular, uniform, fracture process zone changes enormously. That actually the process zone also changes shape. Fracture in concrete, for example, fracture energy doubles at if the compression is half of the strength, but it can go to near zero if it approaches the compression strength. And this was verified for other materials too, actually, for fiber-reinforced concrete. And so I think that's something that needs to be added. The test is quite simple, and I think it will be very interesting to see what's happening in shale. And there will
Absolutely.
be a big difference from granite too.
Yeah, absolutely. So you said this was the GAP test? Gap test?
GAP, yeah, that was published in
Okay.
PNAS Proceedings of National Academy of Sciences 2020.
Oh,
And that's a
absolutely.
simple device where you take a 3-point bend specimen which you use with a notch in the center, and you put the end supports with a gap. And the initial loading is introduced by putting elastoplastic pads next to the notch. So you first load by uniform compression. And when the gaps go to yielding, constant stress, then the gaps close, the bending moment, and crack is growing. And what is beautiful is that the initial state and the final state also statically terminate, because when the force is constant from the yielding pads, there's the same thing as gravity load or something. So it's easily interpreted. A number of people do it, but not in this field already.
Okay, I will take a look at that. That sounds it might answer a lot of questions I've had as well about sort of where this process zone even is in relation to everything. Thank you so much.
Also, it'll change the poromechanics transfer, of course, because when you introduce hydraulic fracture, the overburden is transferred from solid to fluid.
Yes, absolutely.
And that transfer is at first only at the face of the fracture, and it dissipates, and generally in poromechanics is always neglected. I have not seen it ever considered. That's a significant effect.
Yeah, absolutely.
So
I think
maybe
one of the large. Sorry.
Yeah. So go ahead, Bing.
I was just saying that one of the big barriers from my perspective in incorporating form mechanics is that the permeability becomes so heterogeneous within this micro scale that it's very difficult to sort of get it to work with a single value. So we need tomography basically coupled with the kinds of experiments that I showed, I think, to get a good idea of what the pore mechanics looks like. I think that's one of the big things. Yeah.
I think in the interest of time, we have one more question. And Ed, I'm sorry, I'm going to skip you. And Omar, I'm going to skip you. I'm just going to go right to Hafiz. Hafiz is interested in the inSAR. And how are you able to estimate the surface displacement relative to subsurface pore pressure changes? Were you only looking at surface displacement? How could horizontal displacement better improve the modeling?
Absolutely. So I didn't mention this, but the inSAR data is actually only single track. I think it's either ascending or descending. So it's actually only line of sight. It's not even vertical displacement. It's sort of an oblique displacement. So what we've done is when we construct our model and we model the surface displacement, we are only decomposing that into the direction of the line of sight. So we're comparing apples to apples in this case, only along that given direction. But absolutely, if we were to have horizontal displacements, that would help to, we would have more constraints essentially on our model, and it would help a lot. I didn't show this, but there's a lot of non-uniqueness problems with these hydromechanical properties that we calibrate. And so having both inSAR tracks would be absolutely wonderful to have.
You've had a lot of questions, but maybe just in the interest of time, I will compile the questions from the chat and forward them to you, and you can respond directly to these people if you have time.
Sure. Or if yeah, I can stick around too if people wanted to have a more informal discussion. Either way is fine with me.
By all means, we can do that. But regardless, I would like to thank you for a really tremendous and informative talk, and I would like to thank everyone for attending.
Yeah, thanks everyone for coming.
And Bing is available to stick around to answer additional questions. So Ed, Omar, I know you have questions on the board. Just speak up.
All right. So Bing, really great talk. A lot of the work I was familiar with, and a lot of the work is new to me, and it looks just as interesting as ever. I had two questions. One is like very broad definition and description of seismic versus aseismic. Do we have a good understanding of what makes a material aseismic? From things like ductility, grain size, cementation, anything like that.
Yeah, so sorry, or can I do one by one? Because that was a
let's
long
do
one.
one by one. Sure.
Okay. So seismicity, aseismicity, one of the classic papers I was looking at was from Mark Zobak's group. I think it was Zobak and Foley. And really what they argue that drives this is this A minus B parameter, which is the rate and state parameter. And this describes whether material, when it begins to slip, whether that forms sort of a negative feedback loop that it slips and it slows down as it slips more, versus a positive feedback loop where if it starts to slip, it slips even faster. So for materials like granite, it tends to be rate weakening. So as it slips faster. And this is what causes this sort of fast, rapid seismic deformation. Whereas in shales, especially those with high clay content, or clay or organics content, one of those. This is what was in the Coley and Zobak paper. They show that as, again, either clay or organic content increases, it turns into a rate strengthening mode. That is, it'll tend to creep, right? As it creeps, it actually slows down. So it'll sort of slowly deform over time. That's sort of the main definition, I guess, if you will, between seismic and aseismic.
All right, thanks for that. And the other question I had was regarding your usage of time throughout the presentation. You use like T-norm and predicting breakdown time and time to failure. And I know you like using energy. And here we're talking about inputting energy and then releasing energy. So I guess the question is, like so if you have a constant input, I guess using time is fine. But what if your input were to vary? How would that change things?
Absolutely. So I think with let's go back. So for example, here I'm using time as the so were you talking about this one or a different one?
Yeah, I mean, this is one of the examples, sure.
Yeah, so we could, so I was looking at the time series of the acoustic emissions as the input. But you could very easily do the same to the pressure, right? You could use the pressure and the characteristics of that pressure as the input, as opposed to using the acoustic emissions. The only issue here is in terms of time resolution, right? This we have 5 megahertz sampling. The pressure we have 100 hertz sampling, right? You get a lot more from this because we have a lot more of it, basically. That's the main advantage. Yeah, but with these models, you can throw in whatever you want, as long as you have enough of it.
Okay, so just to clarify.